Yeah, well, that's my team work. I begin. I will say some definitions. A topological graph is a graph with an embedding on the plane, which is vertices are represented by distinct points, and the edges represented by Jordan arcs connecting pairs of vertices. A geometric graph is a graph in which its vertices are represented by points and the plane, and its edges by a straight line segment joining pair of vertices. A planar graph is a graph that can be embedded in the plane in such a way that its edges may intersect only at their endpoints. A plane graph is a planar embedding of a planar graph. We say that two or more geometric graphs are compatible if their union is a plane geometric graph. Here's an example. Two geometric graphs, and their union is a plane geometric graph. This term is used in this paper of Alfredo Garcia et al. We say that the neighborhood of B is saturated if there is no edge that can be added to G incident to B and avoiding edge crossing. In the example, we have an edge and dashing edge that cannot be added, avoiding the crossing. For short, we say that B is not saturated and B is saturated. We introduce this problem, and the problem say that given a topological or geometric plane graph G and a set parity constraint C, where each Bi in B has assigned the constraint Ci to augment the problem to meet parity constraints if that finding a set of H E prime where E prime intersection E is empty. This is an example. This is my set of vertices. This is my set of parity constraints. You see that the vertex B1 is the odd degree in the constraints have to be odd. The vertex 2 is the odd degree, but in the constraint has to be even. All the vertices that we can change the parity, it's in the set of P, and the vertex in P we represented in the rest of this presentation with empty disks. This is an example of augmentation. We study simple graphs, and the vertices in P must be not saturated. Okay. Our first result, if we have a topological plane tree T, and T is not a star, well, T can always be augmented to meet its parity constraints in order n time with the addition of at most k over 2 plus 1 edges, where cardinality of P is k. The proof is that let T prime be the minimal topological connected subgraph of T containing all the elements in P. And if T prime is, if T prime is a star, we can solve it taking a vertex of T and join the center of the star with that vertex and joining with another leaf of the T prime and joining the rest of the vertices. But if T prime is not a star, we first ask to the each cycle we form must have not have vertices P inside the cycle. First, in the first part of the algorithm, we select two vertices. In this example, B1 and B2. The B1 and B2 have to be an edge distance at least of 3, and we join them. In the second step, we select another two vertices of P, the distance of these vertices have to be at least 2, and we repeat this process. In the last iteration, we possible have this case bk and bk, sorry, this k minus 1 maybe are adjacent, and we have to fix this problem. We have 3 cases for solve this problem. We have to delete this edge, the red edge, and the first case is that if b1 and b2, the edge distance with respect with bk and bk minus 1 is at least 2, we proceed in this manner. In the case 2, without loss of generality, if b1 is distance 1 of bk minus 1, and b2 is a distance of at least 2, this proceeds in this manner. And the last case is that b1 and b2 is at distance 1 with respect with bk and bk minus 1, and we solve this problem adding in this manner the edges. We gave this algorithm if the input is a topological tree, but if the input is a topological graph, the complexity is harder, and we gave a reduction for the planar tree set problem to the problem of deciding if there exists a set E prime with the minimum number of edges, such that the augmentation is a plain topological graph meeting all the parity constraints C while preserving its embedding. Okay, for do this reduction, we built 3 gadgets. This is the basic gadget. The basic gadget has only 2 possible augmentations. These augmentations, we call it the positive augmentation and the negative augmentation. With this basic gadget, we built a literal gadget. We say that it forms a butterfly. If you use your imagination, this is the wings, the body, and the antennae. And it also has 2 possible augmentations. The positive one, I want to note that in the positive one, the vertices of the top are free. And the negative one, and there are no free. We have to join these literals in this manner. The union of 2 literal gadgets of the same variable, negated or not negated, it will join with this extra edges and vertex. This is a right wing of a literal and left wing of another butterfly. And the union forced to, if the augmentation of the literal in the left is a positive augmentation, forced to the augmentation of the literal of the right be positive. And it is the same if the augmentation is negative, this is negative. But if you want to join 2 literals, one non-negated and another negated, we will join with this and some kind of the same. If we have a positive augmentation, we have a negative augmentation, and vice versa. And the third gadget is a closed gadget. This is the antennae of my butterflies. These 2 vertices of my cloth. If at least one literal gadget have a positive augmentation, we can join to these vertices with those vertices of my butterfly. But if don't, we have to use an extra edge, and well, this is the key of the reduction. I think so. This is an example for more clarity. This is a planar tree set formula, and we have an occurrency we have a butterfly for one occurrence of literal. We have 9 literals. We have 9 butterflies, and when you turn the variable t in true, well, the negative is true, and forced to be augmentation the another literals, and so on, and so on, and so on. And well, in this case, the formula it's gonna satisfiable because all my clause is gonna be true, because in all clause there are a positive augmentation. And that's now I'm going to talk about some lower bounds of topological graphs. This lower bound is for some graphs need at least ceil 11 n over 15 edges to be augmented. Okay. This graph have 15 vertices. We want to change the parity of 12 of them, and I want to note that the ellipse can see another vertex in P, and that force that for be augmented you have to use one edge per leaf. Say that augmentation, but the problem is that the 3 vertices inside and the 3 vertices outside, we have to augment it with more edges. We have joined 2 of them, but this one needs 4 edges for be augmented. Okay. For general, we need Pokemon. We need 12 edges to augment this graph, and to generalize this graph, we have consider even triangulation, where an even triangulation is a triangulation that its vertices have even degree. All its vertices have even degree, and in each vertex we have put a copy of the previously graph, and I said you that this graph needs 12 edges for be augmented. But when you put in the triangulation, we can save one. We can eliminate, delete these 2 vertices and substitute with this edge. With that, we do that for each pair of these subgraphs, and we'll have the lower bound. And the next lower bound is because not all the graphs, not in all the graphs, the vertices in P we can change. The vertices in not all the vertices in P we can change the parity, and this is a family we construct. You have a set of pentagons, and you triangulate the exterior of the pentagons. We can change all the parity, all the parity of the vertices of my pentagons, and you can see that only can change 2 per pentagon, and leave 2n over 5 of its vertices. This is the end of the results for topological graphs. I have another lower bounds, but for geometric plane trees. This is the bound for we need 6n over 11 edges for do the augmentation. This example was taken from the paper of Ferran Hurtado and Sabatot. I want to see that H7, H6, H5, H3, B1, and B2, that's the only vertices that see another vertex that are in P. And we join only 4 that vertices. We're going to join H7 and H6 and H3 and B1. And the another 4 remaining vertices because they can see another vertex of P, we have to put an edge per vertex. Doing that and doing that. We need 6 edges, and to generalize this example, we put a copy in the vertex W, and so on and so on. And the next bound is for also the geometric plane trees cannot not always be augmented. And this is the example. We have the vertex B1 and B2, and you can see that if we put this edge for augment the vertex B1, we can put the edge without avoiding the crossing, and well, that's it. Just making a copy and put that, and we have n minus 1 over 10 of its vertices left with their parity unchanged. And thank you. Thank you so much. Yep. Okay.
Okay, so